In this video, we're going to cover section 1.15, diffusion-controlled reactions. Solution phase reactions are very different than those in the gas phase. The number of collisions over time, which is known as the encounter frequency, between reactant molecules dissolved in a solvent are considerably less than in a gas. In addition, two reactant molecules that encounter each other will stay near each other for much longer than in a gas because solvent impedes a molecule's migration away from the location of the encounter. This lingering of one molecule near another on account of the hindering presence of solvent is called the cage effect. Now, these encounter pairs may accumulate enough energy to react even though it does not have enough energy to do so when it first forms. As a result, the activation energy of a reaction is a much more complicated quantity in solution than in a gas because the encounter pair is surrounded by solvent, and the energy of the entire local assembly of reactant and solvent molecules must be considered. So let's consider the following reaction, where we have two reactants in solution coming together to form an encounter pair. And that encounter pair will eventually decay to product. Now, as shown, the only process resulting in product formation is this final step from the encounter pair. So if we derive an expression for the rate of formation, that will be equal to the rate constant K2 and depend upon the concentration of that encounter pair as shown here. So as we've seen in previous examples, the next thing we must do is define an expression for the concentration of this encounter pair in terms of the reactant concentrations A and B. And this is required because this encounter pair, we consider this an intermediate species. So the relationship between the concentration of the encounter pair and the reactants is obtained by writing a differential rate expression for the concentration of this encounter pair and then applying the steady state approximation to it. And here shown is the differential rate expression for that species. And as we would expect, there are three terms in this particular equality because the encounter pair is involved in each of the three steps of this reaction mechanism. It's formed in the first step with a rate constant K1 and dependent upon the concentrations of A and B. It then can undergo consumption in one of two paths. There's the reverse reaction back to reactants with a rate constant K-1, dependent upon the concentration of the encounter pair. And then finally, there's the decay of the encounter pair to product, and that gives us our third term, which is a K2 times the concentration of the encounter pair. So if we apply the steady state approximation to this particular differential rate expression, we can equate it to zero because we know the steady state approximation states just that the net rate of change of the intermediate is approximately equal to zero. So once we have equated that differential rate expression to zero, we can solve for the concentration of the encounter pair, and that's what's shown here. And so we end up with our expression for that particular concentration, and now we can take that solution and substitute it into our expression for the rate of product formation. So we're left with a quotient of rate constants, K1, K2, all over the sum of K-1 plus K2, all multiplied by the concentrations of A and B. And so K effective is going to be equal to that quotient of rate constants. And now we have a rate expression that describes the rate of product formation in terms of our initial reactants. This is the key result of the mechanism for solution phase reactions. It shows that two rate law expressions are possible depending on the relative magnitude of K-1 and K2. This is similar to what we observed when we discussed the pre-equilibrium approximation. And for diffusion-controlled reactions, this sets up the possibility for two cases or two limits based on two conditions, which really is the relative magnitude of these two rate constants. So let's look at those two cases in more detail now. So if the rate constant for the separation of the unreacted encounter pair is smaller in magnitude than the rate constant for its formation into products, that is the condition where K2 is much greater in magnitude than K minus 1, then the rate law expression reduces to the following. And we can see how this comes about. If K2 is much greater in magnitude than K minus 1, then this term is going to be relatively small. As a result, we can see cancellation of K2 as well in the numerator and denominator. And that leads us to a simplified or reduced form, K1 times the concentration of A and B. We refer to this limit as the diffusion-controlled limit, in which the rate of reaction is governed by the rate at which the reactant molecules diffuse through the solvent. So as soon as those reactant molecules encounter one another, the reaction proceeds to product very quickly. And this will be very common in radical type reactions, radical recombination reactions, where as soon as those two radical species come into local vicinity of one another, form that encounter pair, the reaction will occur almost immediately. So if the rate constant for the separation of the unreacted encounter pair is greater in magnitude than the rate constant for its formation into products, that is, K minus 1 is greater in magnitude than K2, then the rate law expression reduces to the following, where we have K2 disappearing from the denominator, leaving us with a composite of rate constants where we have a ratio of K1 over K minus 1, which we can express as the equilibrium constant multiplied by K2, which is the rate constant responsible for the decay from the encounter pair to product. Similar to the diffusion-controlled limit, we see that we still have a second-order overall rate law with a first-order dependence on each of the two reactant concentrations, but we refer to this limit as the activation-controlled limit because the rate of reaction depends on the equilibrium concentration of the encounter pairs and the rate at which energy accumulates in these pairs from the surrounding solvent. This arises when a substantial activation energy is involved in the reaction from the encounter pair to product. So for the remainder of this video, we're going to look at a way in which we can calculate K1 in the diffusion-controlled limit. So the rate of a diffusion-controlled reaction can be calculated by considering the rate at which reactants diffuse together. So let's suppose that molecules of A and B in solution react immediately when they come within some critical reaction distance of one another. We'll refer to this distance as R star. And the rate of reaction is controlled by the rate of encounters between A and B molecules as they diffuse together. With this in mind, the rate constant for this diffusion-controlled reaction can be given as follows, where Kd is equal to 4 pi R star dNA. And so let's define these terms. R star is the critical reaction distance, and in a couple slides, we'll show a diagram that represents what that distance actually means. In general, it's the sum of the radii of the two molecules involved in the reaction. D in this case is the sum of the diffusion coefficients for the two reactants in solution. And this is something that's often overlooked, is that D is not a particular diffusion coefficient for a single molecule, but is the sum. And here's an example. For molecules A and B, it would be the diffusion coefficient with respect to A plus the diffusion coefficient with respect to B. So if we're looking at the reaction between A and B, we must sum those diffusional coefficients. If it was looking at the reaction between two like molecules, then that would be treated as dA plus dA or dB plus dB. And finally, Na is the Avogadro constant. Now, there's actually another way in which we can calculate this diffusional rate constant without really having a clear idea of the identity of the reactants, and I'll explain that now. So the Stokes-Einstein equation, which is shown here, describes the relationship between the diffusion coefficient and the viscosity of the medium, so the viscosity of the solvent in which the reaction is taking place. As you can see, we have a variety of terms. We have kBT, so it's dependent upon the Boltzmann constant, as well as the temperature at which the reaction is being carried out at, and eta, which represents the viscosity of the medium, as well as the hydrodynamic radius of the molecule, which is given as R subscript I, where I is some molecule. So if we incorporate this equation into the expression for the diffusion-controlled rate constant and include the hydrodynamic radius Ra and Rb for each molecule in a medium of viscosity eta, this is what we're left with. The numerators are identical, dependent on temperature and the Boltzmann. The only difference in the denominator is the hydrodynamic radius of the specific reactant. Now, we can approximate this particular hydrodynamic radii for both species. And we can do that using this idea of a critical reaction distance. So if we say to a good approximation that the hydrodynamic radius of A and the hydrodynamic radius of B are roughly 1/2 this critical reaction distance, we're going to see a simplification of these expressions. And so let's look at that. So here is the diagram representing what we mean by this critical reaction distance R star. It's roughly 1/2 of the radii for each of the individual reactants. So if we substitute in for the hydrodynamic radius of A and B with 1/2 R star, the expression for the diffusional coefficient for A and B become equal and are both equal to kBT over 3 pi eta R star. Now, if we sum these diffusional coefficients, we're basically taking this term and multiplying by 2. And so we end up with the sum being equal to 2 kBT over 3 pi eta R star. So now let's substitute this expression into the original expression we used to calculate the diffusional rate constant. So in doing so, we end up with the following. This is our original expression. We're going to substitute in for the sum of the diffusional coefficients, which we said previously is now 2 kBT over 3 pi eta R star. We're going to see cancellation of R star, pi, and we're going to multiply the constants. So we have 8 over 3 multiplied by kBT over eta multiplied by the Avogadro constant. Now we can reduce this even further because the molar gas constant can be calculated or is equal to the Avogadro constant multiplied by the Boltzmann constant. So now we have an expression for the diffusional rate constant, which is simply equal to 8RT over 3 eta. So what this shows us is that we can calculate the diffusional rate constant for any reaction in solution, so long as we know the temperature at which we run that reaction and the viscosity of the solvent for which it's run in. So this expression doesn't rely on having any information with respect to the relative identity of the two reactants, i.e., what the size of these reactant molecules are. And the reason why this approximation works quite well is because although the diffusion coefficients are smaller when the radii are larger, the reactive collision radius is larger for those larger molecules. And so the molecules only need to travel a shorter distance to meet. And the opposite is true for a small molecule. A small molecule, yes, is going to move through solvent more quickly, but its reactive collision radius is smaller, and so it's going to need to travel a larger distance in order to meet the reactant in solution. So you have this balance between size and diffusion through solvent that allows for the hydrodynamic radii to cancel in this way. So in this approximation, the rate constant is independent of the identities of the reactants and depends only on the temperature and viscosity of the solvent. So here we've shown two ways in which we can calculate the diffusional rate constant. If we have information with respect to the diffusional coefficients and the critical reaction distance, then we can calculate it using this expression. However, if the only information that you have with respect to the reaction is the temperature at which it's being run and the viscosity of the solvent, then this expression can be quite useful. So let's look at a couple examples where we use these expressions to calculate the rate constant for a diffusion-controlled reaction. So in this example, we're asked to calculate the diffusion-controlled rate constant in molar units at 298 Kelvin for the recombination of iodine atoms in hexane, which has a viscosity of 0.326 centipoise. Now, the coefficient of viscosity, eta, is often reported in centipoise. So because we're only given temperature and the viscosity of the solvent, that would alert you to use this equation to calculate the diffusional rate constant. So if we input our temperature and our viscosity, we can calculate our diffusional rate constant. Now with these questions, there are unit conversions that you must carry out. So for example, joules we need to convert to kilogram meter squared seconds minus 2. Centipoise we have to convert first to poise and then from poise to kilogram meters minus 1 seconds minus 1. So when we calculate out this particular value in our units, we'll get cancellations. And a meter to the square minus a minus 1 gives you meter cubed. And a seconds to the minus 2 minus a minus 1 will give you seconds minus 1. So this is what we get from that calculation. We get a value of 2.02, carry the 6 for rounding, times 10 to the 7 meters cubed, mole minus 1, seconds minus 1. Now this is not in molar units. We like to convert our rate constants to the same units that we've used previously. For a second order reaction, that would be molar minus 1, seconds minus 1. So we need to convert the cubic meter to liter, and the conversion for that is 1,000 liters is equal to 1 cubic meter. That leads us to a value of 2.02, carry the 6 times 10 to the 10, liter mole minus 1, seconds minus 1. And finally, after rounding, our diffusional rate constant is 2.03 times 10 to the 10, molar minus 1, seconds minus 1. Experimentally, the diffusional rate constant was determined to be 1.30 times 10 to the 10 molar minus 1 seconds minus 1. So the same order of magnitude as what we just calculated. And so the agreement with the experiment is quite good considering the approximations involved in the derivation of this equation. So let's look at an example where we use the other expression to calculate the diffusional rate constant. So suppose that the diffusion coefficient for a reactant in aqueous solution at 298 Kelvin is 4.2 times 10 to the minus 9 meters squared seconds minus 1. If the critical reaction distance is 0.50 nanometers, what is the rate constant for the diffusion-controlled reaction? Again, in molar units. So because you're given a diffusion coefficient for a reactant and a critical reaction distance, that would alert you to use this expression to calculate the diffusional rate constant. So if we substitute in for our critical reaction distance with 0.50 nanometers, we need to convert that to meters using the conversion factor 1 meter is equivalent to 10 to the 9 nanometers. As well, D is equal to the sum of the diffusion coefficients. And so because we're only given one diffusion coefficient, we're assuming that we have a reactant that is in effect reacting with itself. And so we must multiply the diffusion coefficient by 2. If we were given two different diffusion coefficients for two different reactants, then we would sum those values. And then finally, we have the Avogadro constant. So when we calculate through, we end up with 3.1, carry the 7 for rounding, times 10 to the 7 meters cubed, mole minus 1, seconds minus 1. We again use our conversion factor to convert this number into molar units. That gives us 3.1, carry the 7 times 10 to the 10, liter, mole minus 1, seconds minus 1. And after rounding, our diffusional rate constant is 3.2 times 10 to the 10, molar minus 1, seconds minus 1. So if you have any questions about diffusion controlled reactions, whether it's regarding the limits of reactions in solution or the calculations for the diffusional rate constant, by all means, send me an email. Thank you.